So hydrogen is the first metal in the periodic table, which means it has an atomic number of 1. That implies that it only has 1 proton. Hydrogen, also, if you look at its atomic mass is 1.00 something. So that implies that it does not have a neutron. The vast majority of elements, okay, every element except hydrogen, are going to have protons and neutrons in their actual nucleus. Now, we didn't learn about the neutron, and we're not going to, but when a hydrogen bonds to, let's say we've got our chlorine, which is going to have 17 protons in its nucleus. It's going to have 17 or 18 or more neutrons, whatever, we don't care. But that implies that in its orbits, right, because it's going to have 3 shells, it will have 7 electrons on its outermost shell, right? So when hydrogen and chlorine come together, they do bond very readily because hydrogen has 1 electron in its outermost shell, its only shell, and chlorine has 7. So when they actually bond, this guy right here goes over to the actual chlorine, and this ends up leaving hydrogen with an uneven or non-neutral balance. Because 1 proton and 1 electron cancel one another out, but if the electron is lost, then you're left with 1 proton. Okay? So this is where we get the idea of H plus as an ion. It becomes an ion when it gives up its electron, right? So it's no longer balanced. Ions have a positive charge if they've got more protons than electrons, or a negative charge if they've got more electrons than protons. Okay? So to measure the degree of, or the amount of hydrogen protons in a substance, we see that the more hydrogen protons, the more of these guys that are in a substance, the more acidic the substance becomes. That's why in the last video, we talked about the fact that hydrogen is, our H pluses are acidic and they're electrolytes. They're electrolytes because they have a charge, which means they conduct electricity. And we identify chemicals, or we identify chemical formulas as acidic or acids when they've got H's in them. Okay? So the more H's you have, all right, the more acidic you're going to be, the lower your pH will be. Because when we actually talk about the pH scale, we're measuring the number of hydrogen protons we have. So if we look at the pH scale, we know that the pH scale starts at 0 or 1 and it goes all the way up to 14. Now this is a human invention. And it's just a way to classify a behavior or a characteristic of a certain substance. Okay? Testing a substance's pH is just measuring how many protons or H pluses there are versus how many hydroxides or OHs there are. The more hydroxides you have in the substance, okay, the more basic it is. The more H's you have in the substance, the more acidic it is. Okay? And we're going to, as we move on to this, we're going to then talk about how acids and bases interact with one another. And they can actually neutralize one another. Okay? They can cancel out the acidity or the basicity of a substance. So we'll get into that later. But here, we're going to talk about the pH scale. So we're going to start with acids. We know that smack dab in the middle of the pH scale is number 7. Okay, that is what we consider a neutral substance. All right, as we move on this screen to the left, the numbers are going to get smaller. So 1 to 6, let's say, or 0 to 6. As we move to the right, the numbers get bigger. Okay, so 8 to 14. So if we start off with the acids, okay, as we get further away from 7, we're going to see that the amount of hydrogens is going to increase. All right, and I'm using this little diagram to show that the arrow pointing up here at the end where 0 is a much longer arrow than, let's say, where number 6 is. This implies that 0, something with a pH of 0 or 1, is going to have a great deal more hydrogen in it than something that has a pH of 6 or 7. Okay, so if we look at the length of the arrow, from 0, the arrow gets smaller and smaller as we get closer and closer to the middle. Okay? That means that, so 1, 2, 3, 4, 5, 6, and then neutral is 7. So 13, 12. So as we move to the left on the screen, we're getting more and more hydrogen ions, H pluses. Okay, a higher amount of H plus. As we move to the right on the screen, we're getting more and more OHs. Now these two are opposite one another for a lot of reasons. OHs are identified, or they help identify a substance as a base. So these guys, number 14 over here, has little to no H's in it. Okay, it has almost no H's. Another way of looking at this graph, if you want, is you can actually say something like this. You can actually start down here with this guy having an unbelievably large amount of hydrogens, and this guy having an unbelievably small amount of hydrogens. Okay, and when I say that the actual pH scale is logarithmic, I mean that it works with the idea of the power of 10. Every step along the pH scale is a factor of 10. Okay, so one step further away is 10 times more acidic or more basic. 2 steps is 10 to the power of 2. It's 100 times more. And this works its way all across the actual scale. So if we look at our pH scale, okay, which we've drawn in black, 7, which is neutral, is going to be equivalent to 10 to the 0, which means it's got neither, okay, it won't have any H's in it, or it shouldn't have any H's in it that are acidic, and it shouldn't have any hydroxides in it that are basic. But let's do the acids first. As we move down, okay, we're going to go from 7 all the way down to 0, and we're going to use a power of 10. So if we look at something that is a pH of 6, it will actually be 10 to the 1 time more acidic than something that is neutral. So all of these numbers are going to be in relation to 7, pH of 7, which is 10 to the 0. Okay? So we're going to work our way down we're going to work our way to the left from the middle, and then we're going to work our way to the right from the middle. So if we look at the idea here that the further away from middle, from 10 to the 0 that we go, from a pH of 7, the further away from that to the left on the scale means the more acidic something is. So something that has a pH of 0 will be 10 to the 7 times more acidic than something that has a pH of 7. That's a lot more acidic. Okay? That's like 10 million times more acidic. That's a lot. The same thing happens as we move to the right on the pH scale. But in this case, we're going to use negative exponents. So something that has a pH of 8 is going to be 10 to the negative 1 times less acidic than something that is neutral. Okay, and this works its way all the way to the end. So what do you think a pH of 9 would be? Exactly, and this is going to work all the way to 14. So just to show you, something that has a pH of 1 is going to actually be, in real numbers, not exponents, is actually going to be 1,000,000 times more acidic than something that is neutral. So let's do the exact same thing on the other side. We know that in comparison to something that is neutral, something that has a pH of 1 is going to be 10 to the 6 times or 1,000,000 times more acidic than something that is neutral. The same idea occurs when we move to the right, only we're going into infinitely small numbers here. Okay, we're going to have a period or a comma and a lot of zeros before we get to our 1. So if we take a pH of 13, this ends up being 10 to the negative 6, which is 0.1234561. Okay? So we can see that this is the idea of the scale being logarithmic. And if somebody is to ask you how many times more acidic is one substance versus the other, you can't just hop along here and go, if I say I have a substance with a pH of 2, and I want to compare it to a substance with a pH of 6, and I ask you how many times more acidic, you can't just sit here and hop 1, 2, 3, 4. Oh, well, it's 4 times because it's 4 hops. That idea is wrong. It is 10 to the 4 times more acidic. Okay? The little hops here, if you want to work that way, that's fine. But the hops become the exponent number. The number of hops that you have to make from one substance to the other become the actual exponent on your 10. And if you want to double check your work, you punch that into your calculator and it will give you your number. If we're actually looking at this, when we actually talk about your negatives here, okay, and when we actually talk about your exponents, we start off, all right, and we make our way. What you can actually do here is you start off with 10 to the 0 here and you work your way all the way up. Okay, you get smaller and smaller and smaller to 10 to the negative 14, which means this is your base. Start means you got a certain number of hydrogens, and every hop you get, pH of 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, you're getting less and less and less and less and less hydrogens. Okay? Now, I showed you this, and I used my neutral as my starting point. The textbook shows you a pH of 0 as a starting point, and it just gets... So remember that line that I had drawn from here, and I went all the way up? Okay, this has the most hydrogens. Everything after it has a power of 10, less, 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 less. That's another way of comparing the pH scale. Okay? What you need to take away from this is that every hop on the pH scale is a power of 10. All right? That's what you need to take away from this. So things can be more acidic or more basic. You could even say a question could be, okay, let's look at these guys here. How many times more acidic is something with a pH of 9 than something with a pH of 11? How many hops? 2. 10 to the 2. Okay, so we would say that even though these are considered bases, all right, they still will have a small infinitesimal amount of hydrogen ions in them, but 10 to the 9 will have more than 10 to the 11. Okay, or pH of 9, will have more than a pH of 11. It will have 100 times more.